Welcome to AI Paper Podcasts. Today's paper is RubricBench, aligning model-generated rubrics with human standards.
And we're just going to jump right in?
Yeah, no preamble today. The 60-second summary starts right now. So the problem we're facing is that reward models, the systems we use in AI alignment, are hitting a massive wall.
Right. They suffer heavily from verbosity bias and reward hacking.
Exactly. They frequently reward these long, highly polished, but ultimately incorrect or just off-spec answers.
So to fix this, the whole industry is shifting to rubric-guided evaluation, basically using checklists.
But the existing benchmarks are outdated. They completely lack human-authored ground truth.
And to the solution, researchers from City University of Hong Kong, Tencent Hanyu, and others built RubricBench,
which is this amazing data set of 11,147 complex pairwise comparisons, all armed with expert annotated instruction-derived rubrics.
And the key findings are just a total wake-up call. First, there's a massive 27% rubric gap between human-authored rubrics and model-generated ones.
Second, throwing more compute at the models doesn't fix their rubrics. It actually degrades performance through noise.
While human rubrics scale beautifully with compute.
And the root cause of all this is cognitive misalignment. Models can check explicit rules, but they fail entirely at capturing implicit human intents.
Like epistemic modesty.
Yeah.
Just knowing when they shouldn't guess.
Right. So transitioning here for a second, if you were listening to this as an AI researcher or an ML engineer, this paper fundamentally challenges how you evaluate model alignment.
It really does. It upends the assumption that we can just trust language models to write their own grading rubrics.
Okay, so let's unpack this from the beginning. For anyone listening who is actively working on alignment, you know how crucial reward models, or RMs, are.
Absolutely.
But to understand why RubricBench is such a necessary breakthrough, we should probably trace how we got here. How did the early days of RMs set us up for this specific bottleneck?
Well, in the early days of alignment, the standard approach was using what we call scalar RMs.
Right. Just the single score.
Exactly. Imagine a model acting as a judge, and its only job is to look at a response and spit out a single opaque score.
No explanation, just a grade at the top of the paper.
Just a raw number representing a thumbs up or a thumbs down. And because that score lacked any transparency, it invited the models to exploit spurious correlations.
Reward hacking.
Exactly, reward hacking. The AI generating the text would realize that certain superficial traits reliably resulted in a higher score from the scalar RM.
So if it used a highly polite tone or
if it just generated a massive wall of text, the judge would give it a top grade regardless of whether the content was actually factually correct.
Or even useful to the user. It sounds like a student who doesn't know the answer on a test, so they just write a 10-page essay filled with buzzwords.
Hoping the teacher gets exhausted and gives them an A?
Yeah.
Yeah, that's verbosity bias in a nutshell.
So when the field realized these single-number scores were causing models to sound smart without actually being smart, what was the next move?
Well, the pivot was the LLM as a judge paradigm, specifically using generative RMs.
Forcing them to show their work?
Right, mandating a chain of thought. Instead of just giving a number, the model had to actually write out a rationale for why it was giving a specific score.
The assumption being that if you force it to reason through the evaluation, it'll make better objective choices.
But without strict objective constraints, generative RMs just tend to invent post hoc rationalizations.
They still make the biased choice.
Exactly. Maybe they subconsciously prefer the markdown formatting of response A, but because they have to explain themselves, they fabricate this highly convincing, articulate, but totally flawed critique.
To justify the initial biased choice, they write a great essay about why the wrong answer is right.
Which leads us to the current paradigm, rubric-guided evaluation.
Right, because if free writing their reasoning leads to post hoc rationalization, you have to restrict them.
You break down vague quality definitions into atomic Boolean constraints. True or false checklists.
Did it answer the prompt? Yes or no. Did it avoid jargon? Yes or no.
It anchors the evaluation in objective criteria. But this exposes a glaring missing piece.
Despite this huge shift, the community had no way to rigorously test it.
Which is exactly what the authors of RubricBench identified.
But wait, if this is the standard approach now, how could we not test it? Don't we have established benchmarks like RewardBench or Help Steer?
We do,
Yeah.
but they fall short for this specific architectural shift. They suffer from two major problems.
Lack of discriminative complexity being one.
Right. They use outdated, trivial prompts that any modern LLM can ace. So they don't actually test the judge's ability to discern subtle errors.
And more importantly, they completely lack human-annotated reference rubrics.
There's no ground truth.
So if I'm an engineer asking my model to generate a checklist for a coding task, I have no idea if the checklist it makes is actually good.
You can't measure the gap between what your AI thinks is important and what a human expert thinks is important.
And that is exactly what RubricBench solves.
Yep. 11,147 curated preference pairs.
And let's dig into how they built that, because the multidimensional filtration pipeline is where this gets fascinating.
They didn't just scrape random data. They filtered for the hardest deceptive samples across 3 dimensions. The first is input complexity.
So prompts with both explicit and implicit constraints.
Right. Not just list 3 reasons, but underline rules humans intuitively grasp.
The paper uses a great analogy for this, the grandparent example.
Oh yeah, it's a perfect illustration.
If the prompt says, explain blockchain to my grandparent, the explicit constraint is explain the topic.
But the implicit constraint, the unspoken rule, is that you absolutely must avoid technical jargon.
The user didn't explicitly type no jargon, but any human knows that's required.
Exactly. Then the second filtration dimension is output surface bias.
Which targets the exact vulnerabilities we talked about with reward hacking.
They force the judge to choose between a short, compliant answer and a highly polished, formatted, but off-spec answer.
It's the shiny garbage. And models usually fail here and pick the shiny garbage.
Every time. And the third dimension is process failures.
Comparing valid reasoning against outputs that look logical but contain hidden hallucination steps.
Deep in the math or the logic. It's insidious.
So we have these 11,147 incredibly tricky pairs. But the gold standard here is the annotation.
Right. Every single pair in RubricBench is augmented with a human-annotated rubric.
Derived strictly from the original instructions by experts, it's the ultimate answer key.
Having that ground truth is revolutionary for running rigorous experiments.
And here's where it gets really interesting. Let's look at the baseline reality check.
The numbers are pretty stark.
When they tested standard LLM judges like GPT-4 Mini and Scalar RMs, they stagnated at around 40 to 47% accuracy.
On these highly deceptive pairs, they're basically performing worse than a coin flip.
Now, when they used rubric-aware RMs, it reached a distinct but still low tier of about 58%.
So using rubrics helps, but 58% is still failing.
Which reveals the massive 27% rubric gap between using model-generated rubrics and human-annotated rubrics.
Models aren't failing because they can't check boxes. They're failing because they're writing terrible boxes to check.
And this ties into a huge trend right now, using test-time compute scaling. Figure 3 from the paper.
This is perhaps the most fascinating finding.
Because the logic is usually if a model's first answer isn't great, you give it more time to generate options or critique itself.
Like giving a student extra time on a test, they usually catch their mistakes.
But scaling compute completely fails for AI rubric generation.
It backfires. When you ask a model like GPT-4 Mini to scale from generating 4 rubrics to 32 rubrics, accuracy actually drops.
From 48.0% down to 46.8%, adding iterative refinement loops literally hurts performance.
They just accumulate noise, they second-guess themselves and write irrelevant rules.
But conversely, when you scale compute using the human rubrics, the accuracy skyrockets.
Gemini 3 Flash jumps from 75.4% to 85.3%.
If we connect this to the bigger picture for engineers listening right now, the takeaway is massive.
The bottleneck isn't compute. It's not reasoning power at inference time.
It's the structural soundness of the rubric itself.
Exactly. If your foundational checklist is missing the core intent, no amount of compute will save it. You're just optimizing a flawed premise faster.
Which brings us to the root cause. Why are these advanced models so bad at writing a simple grading rubric?
The researchers call it cognitive misalignment.
Models are great at checking explicit rules.
If you say, write a poem in exactly 4 lines, they'll add must be exactly 4 lines to the checklist.
But they fail entirely at capturing implicit human intents.
Like the interest rate example from the paper.
Let's unpack that because it makes this so concrete for the listener.
Imagine a math prompt asking to calculate a return, but it's missing the interest rate.
The human rubric applies epistemic modesty.
Right. A human knows the AI shouldn't just guess. It checks if the model detected the ambiguity, asked the user for the rate, and avoided guessing.
But the model-generated rubric does the opposite, assumption injection.
It invents a random interest rate. It says check if the math is correct based on a 5% rate.
Completely missing the fact that the parameter was fabricated. It prioritizes calculating any answer over being honest,
And they quantified this failure using structural F1 metrics.
which measure how well the model's checklist matches the human's checklist structurally.
Both precision, are the rules relevant, and recall, did it capture all the necessary rules?
And the hallucination rates are shocking. For instance, the check-evil framework has a 68.7% hallucination rate.
Nearly 70% of the rules it generated didn't match any human constraint.
It's evaluating based on completely irrelevant fabricated criteria.
But to prove the evaluator isn't the problem, they did a human study.
Right, because skeptics might say, well, maybe the LMM judge is just bad at reading the checklist.
So they had human annotators use both rubrics. Humans using human rubrics hit 92% accuracy.
But humans forced to use model-generated rubrics dropped to 61% accuracy.
Proving that the rubrics themselves are fundamentally broken and misleading.
So what does this all mean? If you are an ML engineer relying on LLM as a judge to evaluate your alignment, and you are letting the model write its own rubrics, you are optimizing for a fundamentally misaligned target.
You're rewarding surface-level polish and punishing true human intent.
I want to leave you with one final thought to ponder. If state-of-the-art reasoning models inherently lack epistemic modesty and cannot deduce the implicit unwritten rules of human intent from a prompt,
Can we ever solve alignment simply by feeding these models more data?
or does this prove we need a fundamentally new architectural approach to capture the deep cognition of human intent?
It's a question the whole field needs to reckon with.
Absolutely. Thank you for joining us for this breakdown on AI paper podcasts.
See you next time.